take a second and look at the metal objects around you right now.
Yeah, literally anything.
Right? Maybe there's a heavy-duty wrench sitting on a workbench, or, a premium chef's knife on the kitchen counter, or even just the structural stuff, like the components locked away inside your car's engine.
Most people just see gray metal.
Exactly. We tend to point at these things and simply call them steel, right? We just assume they are these static, uniform, perfectly solid blocks of material.
Which is, it's completely wrong.
Yeah, because if you zoom in, those tools are, well, they're microscopic battlegrounds. They are defined by these invisible atomic forces constantly fighting for dominance under extreme stress.
It's a completely different reality at that level. To the naked eye, sure, a steel beam looks inert. But if you put it under a high-powered electron microscope, it is this highly engineered combat zone.
Oh, absolutely.
You're looking at a constantly shifting matrix of metallic crystals and these complex compounds that are just, pushing back against immense mechanical and thermal loads.
And our mission for this deep dive is to drop right into the middle of that combat zone. We are looking at a really dense stack of inorganic chemistry textbooks, engineering journals, and metallurgy manuals today.
Heavy reading.
Very heavy. But the goal is to understand why two specific elements completely dominate this space. Vanadium, which is atomic number 23, and molybdenum, atomic number 42.
Yeah, if you are designing high-performance hand tools or engineering aerospace turbines, these two transition metals are the undisputed heavyweights of modern manufacturing. You simply cannot build the modern industrial world without them.
Right, but to truly understand how they forge these near-indestructible alloys, we have to kind of strip away the macro-level engineering first.
We have to look at their raw baseline atomic properties because, the architecture of a skyscraper is dictated by the strength of its individual beams.
Yeah, that makes sense.
So the strength of an alloy is directly dictated by orbital chemistry.
Okay, let's unpack this orbital chemistry stuff. Let's start with molybdenum, sitting in the 4D series of the periodic table. Its electron configuration is 5s145.
Right, which is crucial.
Yeah, for the material scientists listening, that half-filled D shell means maximum symmetrical overlap. But in practical terms, for the rest of us, how does that configuration actually translate to the physical metal?
Well, it translates to an astonishing level of cohesive energy. Molybdenum has 6 outer electrons available for bonding.
Okay.
And because of its specific position in the forward series, those atomic orbitals are the perfect physical size to overlap seamlessly with neighboring atoms.
So they just lock together perfectly.
Exactly. When we plot out the cohesive energy, basically the sheer thermodynamic force holding the atoms together, molybdenum sits at the absolute peak of the curve for its series. It represents this massive energetic well.
So molybdenum atoms reach out, overlap perfectly, and lock together with a grip so tight it takes massive amounts of thermal energy to break them apart. It's like a person with long arms giving a perfect, unbreakable handshake.
That is a great way to put it, which is why pure molybdenum has a melting point of 2,610 degrees Celsius.
Wow.
Yeah, the atomic handshake is fundamentally unbreakable under normal thermal conditions. But when we look at vanadium, sitting in the third series, the physical dynamics change entirely.
Because in the third series, the orbitals are closer to the nucleus, right? The nucleus has a much tighter leash on those electrons.
A very tight leash. The positive charge of the protons pulls those third orbitals inward, which physically contracts the atomic volume. And because the orbitals are pulled in so tightly, they can't reach out and overlap effectively with neighboring vanadium atoms.
So if molybdenum's giving this perfect handshake, vanadium is stuck with, contracted T-Rex arms.
Yeah, exactly, T-Rex arms. So if molybdenum is at the peak of the cohesive energy volcano, vanadium's contracted orbitals drop it into a cohesive energy crater.
The atoms just can't hold on to each other with the same grip.
They really can't. The orbital overlap is incredibly poor. And because those outer electrons aren't being utilized effectively for interatomic bonding, their spins unpair.
Wait, unpair?
Yeah, and this unpairing actually generates magnetic behavior in pure vanadium.
Okay, wait, I need to push back on that for a second. We don't build wrenches and turbine blades out of magnetic pure vanadium. We drop it into steel. So does this magnetic property actually matter to the final listener holding a steel tool?
Yeah.
Or is it just a quirk of the pure element?
It's just a quirk. The magnetism itself doesn't matter to the end product at all. It is just a symptom of the real driving force, which is that ultra-compact, tightly leashed atomic volume.
Oh, okay.
The weak overlap and the cohesive energy crater define how vanadium acts in isolation. But when you drop those contracted vanadium atoms into a blazing hot matrix of iron and carbon, well, everything changes.
Those tight orbitals suddenly find an ideal partner. And that brings us to the actual forge. We know steel is inherently an alloy of iron and carbon. When they combine, they form cementite, or iron carbide. But cementite is brittle.
Right? Very brittle. It's almost ceramic in its hardness.
Right. But when we introduce molybdenum and vanadium into that liquid mix, they don't just passively float around, they actively hijack the carbon to form their own specialized carbides.
Oh, they absolutely dominate the carbon chemistry of the alloy. And they do it in completely different ways, dictated entirely by those atomic profiles we just discussed.
So let's look at the acronyms the journals use, MC and M6C.
Right, so in metallurgy, M stands for the transition metal and C is carbon. Because of vanadium's tightly contracted atomic volume, the T-Rex arms, it forms an MC carbide.
Meaning a 1-to-1 ratio.
Yeah.
One vanadium atom locks onto one carbon atom.
Yes, just 1-to-1. And they arrange themselves into a face-centered cubic crystal. It is a brutally efficient, densely packed microscopic structure.
And that makes it hard.
Insanely hard. These vanadium MC carbides are intensely hard and remain completely stable up to 1260 degrees Celsius.
Wow. And molybdenum. With its massive, cohesive energy and perfect orbital overlap, it must build something far more complex than a simple 1-to-1 ratio.
It builds an M6C carbide. This is a massive, complex molecule where 6 metal atoms, usually a mix of molybdenum and iron trap, a single carbon atom.
6-to-1.
Yeah, so instead of a tight, dense little crystal like vanadium, molybdenum creates this heavy, immovable molecular anchor within the steel lattice.
Okay, let's translate those microscopic structures, the MC crystal and the M6C anchor, into real-world properties.
Yeah.
Because during heat treatment, the steel enters the austenite phase.
Right, the austenite phase.
And austenite is notorious for causing structural problems if it isn't controlled, right?
Highly volatile. If you visualize the austenite grains inside the steel like a tightly packed room full of balloons, heat causes those balloons to inflate.
Okay, I like this analogy.
As the metal gets hotter, the individual grains swell, they push against each other, and they merge. If you allow those grains to grow too large, the final cooled steel will be incredibly brittle.
It'll just shatter under impact.
Exactly. You need the grains to remain microscopic.
Which is where vanadium's MC carbides come into play. If the austenite grains are inflating balloons, the vanadium carbides act like indestructible concrete pillars wedged between them.
Yes. They physically block the expansion. The technical term in the literature is pinning.
Pinning.
Yeah. And the research from the Acta Metallurgica Sinica journal in our stack provides incredible data on this. They studied how vanadium carbonitride particles sit right on the boundaries of these austenite grains.
Because they're so thermally stable.
Right. They don't dissolve, they pin the boundaries in place. The data showed that holding vanadium-alloyed steel at 820 degrees Celsius for 10 seconds locked the grains at an ultrafine 3.98 micrometers.
But 10 seconds is a blink of an eye in a forge. What happens if you leave it baking at that temperature for like an hour? Do the pillars eventually give way?
They hardly budge. After a full hour, that's 3,600 seconds at 820 degrees, the grains only grew by 1.47 micrometers.
That's nothing.
It's nothing. The vanadium carbides practically paralyze the grain growth.
So by ensuring the internal crystal structure remains ultra-fine, vanadium basically guarantees the final metal is packed with dense, tightly bound grains, which translates directly to impact toughness for the user.
It completely dictates whether a tool absorbs kinetic energy or catastrophically fails.
Okay, so knowing how they manipulate the internal architecture of the steel, let's look at the ultimate engineering showdown. If you were designing a high-performance machine, which alloy do you choose? Chromium molybdenum or chromium vanadium?
Team Mo or Team V?
Right.
Well, if the engineering challenge involves extreme sustained heat and persistent stress, chromium molybdenum is the only logical choice. Team Mo is the king of preventing creep.
Let's unpack creep mechanically. Because standard steel doesn't just melt the second it gets hot. What does solid metal stretch?
It all comes down to atomic dislocations. In any crystal lattice, there are microscopic imperfections, literally missing lines of atoms.
Okay.
Under sustained stress and high temperatures, these empty lines start to migrate. The atomic planes of the metal physically slide past each other, one microscopic row at a time.
So over thousands of hours, the solid metal actually stretches.
Exactly.
It's almost like pushing a wrinkle across a heavy rug. You move it an inch at a time until the whole rug is shifted.
That is an excellent way to visualize it. Now, put a jet engine turbine blade in that scenario.
Oh, man.
It is spinning at tens of thousands of RPMs, constantly blasted by exhaust heat. If that blade creeps even a fraction of a millimeter, it strikes the engine housing and destroys the turbine.
Which is terrifying. And this is where molybdenum's M6C Carbides do their heavy lifting.
Because those 6-to-1 molecular anchors act like heavy furniture placed on top of that rug.
They just pin it down.
They pin the dislocation lines. When the atomic planes attempt to slide past one another under thermal stress, they slam into these massive, deeply rooted M6C networks, and they just stop.
The structural foundation refuses to yield.
Right. That creep resistance is why molybdenum is non-negotiable for aerospace components, power generation turbines, and high-pressure boiler tubes.
Okay, so that handles the thermal extremes. But if we move away from the turbines and down to the mechanical extremes, I'm going to argue for Team Vanadium.
All right, let's hear it.
Because chromium-vanadium steel thrives in environments of catastrophic physical abuse. Because of those ultra-fine grains pinned by the MC Carbides, CRV steel achieves a massive load-bearing capacity.
An incredible shock absorption. It handles sudden, violent force better than almost anything else.
Right. If you need to put a heavy steel cheater bar on a socket wrench and literally jump on it with your full body weight to snap a rusted bolt loose, you are relying entirely on vanadium.
A standard steel wrench would shear in half.
Exactly. And molybdenum might be too brittle for that sudden shock. But vanadium flexes. It absorbs the kinetic energy across millions of micrograins and holds its shape.
Which makes it the undisputed standard for premium hand tools, automotive gears, and high-end knife blades.
It's everywhere in the garage.
It is. And there is also a pragmatic manufacturing dynamic driving that division, you know. Molybdenum is significantly rarer.
Oh, really?
Yeah, and forming those perfect M6C networks requires precise, highly complex heat treatment cycles. It is expensive.
So it's a cost bottleneck, too.
Absolutely. Vanadium, while still a premium additive, is much more forgiving in the forge. That combination of impact toughness and manufacturing efficiency allows CRV steel to dominate the consumer and industrial tool market.
Okay, so engineering always involves trade-offs. You balance thermal creep against impact shock or cost against complexity. But what happens when an industrial bottleneck is so severe that engineers refuse to compromise?
Yeah.
What happens when you combine both heavyweights into a single alloy?
Well, the results are some of the most advanced, resilient materials on Earth. Our sources detail a fascinating case study on the design of high-speed steel for heavy industrial mill rolls.
Mill rolls. These are massive steel cylinders used to crush and flatten glowing hot metal in steel mills, right?
Yes. They endure nightmarish friction, blistering heat, and crushing physical pressure all at once.
Literally the ultimate torture test. And historically, the sources show engineers relied on tungsten to harden these rolls. But tungsten introduced a fatal flaw during centrifugal casting.
Right, so centrifugal casting involves pouring liquid steel into a mold that is spinning at high speeds.
Like a centrifuge.
Exactly, using centrifugal force to shape the cylinder. The problem is physics. Tungsten is incredibly dense and heavy.
So when they spun the liquid steel,
The tungsten caused specific gravity segregation.
meaning the heavier elements were thrown to the outside edge of the spinning mold, leaving all the lighter elements on the inside?
Which destroyed the uniformity of the alloy. You would end up with a mill roll that was ultra-hard on one side and dangerously soft on the other. It was a complete manufacturing nightmare.
So if tungsten's sheer mass is the bottleneck, they had to swap it out for something much lighter that could still form those highly stable, high-temperature carbides. They had to look at our two atomic champions.
They completely rewrote the atomic recipe. They engineered an alloy using 0 tungsten, replacing it with a very specific mix. 7% molybdenum, 7% vanadium, and 2% carbon.
A 7-7-2 ratio. How do the two transition metals interact when they are forced into the same carbon matrix like that?
They divide and conquer perfectly. The manufacturing process for this alloy is intense. They pour the liquid steel at around 1380 degrees Celsius.
Insanely high.
Then they quench it rapidly down to 1190 degrees and run a highly controlled tempering phase at 550 degrees.
And during those massive thermal drops, the elements just go to work.
Exactly. Molybdenum aggressively binds the carbon to build its stabilizing M6C network. It lays down a deep, immovable structural foundation designed to resist the blistering heat of the steel mill.
And then vanadium jumps in.
Yes. Meanwhile, vanadium, with its tight third orbitals, begins seeding the metal with billions of super-hard, face-centered cubic MC grains.
And crucially, because vanadium and molybdenum have a significantly lower atomic mass than tungsten, they don't segregate.
Right. They remain perfectly suspended in the liquid steel while the mold spins.
No gravity segregation. You get a perfectly uniform distribution. The molybdenum provides the red hardness, the ability of the metal to maintain its structural integrity even when it's glowing red hot.
And the Vanadium-MC Carbides provide the phenomenal wear resistance and impact toughness, so the massive roll doesn't crack under the crushing pressure.
It is incredible how a microscopic tweak in an electron shell scales all the way up to millions of pounds of crushing force in the steel mill.
It really is. By analyzing the specific cohesive energy plots and the orbital chemistry of both elements, metallurgists bypass the limitations of tungsten entirely.
They build a customized alloy that outperforms older generations in every measurable category.
It proves that the macroscopic world we rely on is entirely at the mercy of quantum mechanics.
We've traced this from the deepest atomic levels, from molybdenum's perfect overlapping grip and vanadium's tightly leashed cohesive crater. We've seen how they hijack carbon to form these highly specific carbides.
Anchoring the atomic planes against creep.
Right, or pinning the austenite grains to absorb massive impacts. And it culminates in these highly engineered tag-team alloys that literally shape the modern world.
But looking at the industrial scale of these elements brings up a broader context. Beyond the mechanics and the chemistry, there is a global supply chain reality to consider.
You mean the physical cost of actually pulling these atomic heavyweights out of the ground?
Exactly. It's often referred to as the sustainability paradox in metallurgy. Mining molybdenum is vastly more energy-intensive and physically demanding than extracting vanadium.
Right.
You are dealing with deep earth extraction, complex refining, and a really heavy upfront environmental footprint just to isolate the raw element.
But you're trading that heavy upfront cost against the eventual lifespan of the tool or the turbine.
That is the paradox. Because we alloy standard steel with molybdenum and vanadium, the lifespan of our industrial machinery, aerospace engines, and even basic consumer tools is extended by decades.
They just don't break.
The KRMO and KRV alloys refuse to fail. We aren't melting down and replacing millions of broken wrenches every year. We aren't constantly swapping out deformed turbine blades.
So the upfront environmental cost is massive, but the long-term reduction in global waste and material failure is equally staggering.
There's a massive balancing act between extraction, engineering, and longevity.
It really changes the context of that wrench sitting on the workbench, doesn't it? It isn't just a static hunk of gray metal.
Not at all.
It is a highly engineered, microscopic combat zone. It's the product of specific electron configurations, carbon hijacking carbides, and a massive global supply chain constantly balancing the cost of extraction against the relentless demand for human progress.
There is an entire universe of physics, engineering, and economics locked inside every piece of alloy steel you touch.
Something to think about the next time you put a wrench to a rusted bolt and expect the metal to hold. Thank you for joining us on this deep dive into the invisible forces holding our world together. Follow, like, share Atomic 118. Well, in this case, atomic numbers 42 and 23. Keep asking questions, and we will see you next time.